on this computer. All right, we are recording. Awesome. So the session is officially underway. You guys have an exam on Thursday this week, in case you weren't aware. And yeah, it's going to be going over everything since the last test. So LRC circuits are a big component of this, as well as magnetic fields and magnetic forces, induction, all that good stuff, and inductors. Those are on there as well. So I think I usually run these review sessions as a bit of, we just run through a previous exam, practice exam for the class. And what I would like to do is, I usually start these out by going over the formula sheet, because there's a lot of formulas on here, and I think it's useful to be reminded of what they all mean. So this usually takes a decent chunk of time. Let me know if it's not helpful though, because I can speed it up or just skip some stuff. I will skip the first page. Just keep in mind, you don't need to memorize all these powers of tens. So they'll give you oftentimes it's microfarads for units of capacitors. You don't need to memorize what micro is. You have the power of 10 right here. So that's a useful table. Also, the geometry stuff will come into play, especially the perimeter of the circle, when we use Ampere's law. Yeah, and then they've got some useful physical constants here. So we're not going to have fluids on this exam. It should not come up since that was on the first exam. So I'm not going to cover that, but electrostatics, it can be a good idea to remind ourselves. So Coulomb's law, there's a lot of stuff here, but it's not super important that we understand all of these individual parts. We won't be doing electric field calculations anymore. You may have to write it down at some point, but that's not something that's gonna be important. Instead, we need to have a good understanding of what electric flux is, because electric flux is going to be an important part of induction. You remember, so this dE, you need to hold on, I gotta pull up. Here we go. So if we have induction happening, you're going to have to take derivatives of flux. So magnetic flux is the case for Ampere's law, or Faraday's law of induction, I mean.
What was that, dude?
But the idea is we need to understand what flux is. So remember, flux is just a surface, and that surface, each differential area, so just a tiny chunk of that surface, has a vector associated with it. And that vector is pointing perpendicular to that surface. So it can be as curvy as you want, but each individual part has a vector associated with it. And then we have an E field, and that E field is pointing in a certain direction. So we take the dot product of those two vectors. That's going to give us a number. And then we take that dot product at every point along our surface. And then once we do that, then we get a flux out of it. So that works for any field that we have. It doesn't have to be E field or B field. It could be any sort of field. Oftentimes we care about E and B fields though. So that's just a recap of what electric flux is. The rest of the stuff isn't super important except for voltage. Just remember, a voltage is just an integral of the E field over a distance. So if you're confused about the units of the E field, you can always remember it's a voltage. That's what this is right here, divided by a length, because this is going to give a length times E field. So units of that are going to be volts per meter. So on to capacitors. I think we're getting to the new stuff here. This was on the last test, but this will be important. So capacitance is Q divided by V. That's what it is. Remember, it's a geometric quantity, so it only depends on how your capacitor is shaped. It doesn't depend on how much Q is there at the point at a current time, because every time when you do the calculation, it should cancel out. So it is a purely geometric quantity. You want to keep that in mind. Sometimes it's useful to have that Q there when you're doing calculations, but the actual principle of capacitance does not involve having that Q actually sitting on the plates of capacitors. The capacitance is independent of that. All right. So this formula right here, C is equal to epsilon naught times A over D. So this is for parallel plate capacitors. A is the area of the plates, D is the distance between them. And then we have these are just different kinds of capacitors. So this is the capacitance for a cylindrical capacitor. This is a spherical capacitor, and this is a spherical capacitor with the second shell at infinity. So you just take the second shell and make it infinitely large. So it's essentially the capacitance of a single sphere without a second layer to it. This is surprisingly important because if you look at the magnetostatics portion, there's nothing about magnetic materials that I could find at least. So what you want to keep in mind is that these things for capacitance. So remember, if you put a dielectric in between a capacitor, you're going to increase its capacitance by this factor of kappa. And it works the same way for magnetic materials. So that's why it's important, is because if you forget how these work, you just replace this E with a mu, and it'll work exactly the same way. So you might want, it's worth making a note of that since it's not explicitly said on your equation sheet. If you have a magnetic material and you like slide that into a solenoid, that's often the case. You have some sort of a magnetic field going through a region of space, and then you fill that region of space with some kind of material, and that material will have a number associated with it, and that number is kappa. And you just, to figure out what the E field is, do inside of there, you, instead of using mu naught, which we always use for our magnetic field calculations, we're going to use mu, which is just kappa times epsilon mu naught. These are how capacitors combine. This should be pretty familiar with that. And this is just the energy stored on the capacitor. And this is energy density right here. Okay, so now on to electric current and resistor circuits. This shouldn't be super surprising. This is just how resistors work. Rules for how they combine are right here. This is how they change with how resistance changes with temperature, and the definition of current. V equals IR. Hopefully you guys are pretty comfortable with that. We'll be using that often. It's good to just kind of have that in your back pocket. And this is, so V equals IR is pretty much always true in this class, but you know, sometimes you have to be careful when you're applying it, because V equals IR isn't true in AC LRC circuits. You need to use E is equal to IZ, because in those circuits you have reactances that depend on omega. So things are a bit more complicated there. So it's always true in the sense that, well, you know, if you had instantaneous current, then yeah, it would work like that, but it doesn't. If you don't have instantaneous current, it doesn't work nicely. And the rest of the equations are pretty intuitive, I think. It shouldn't come up too often on this test. P equals IV. That is very useful. So remember, power is the rate at which energy is dissipated, and that has to happen for over the resistor. So for an LRC circuit, all your energy is being dissipated at the resistor, because every time we have a capacitor or a inductor, unless stated otherwise, they're assumed to be ideal, which means that no power dissipation can happen there, because all they do is store energy. They don't make it go anywhere. All they do is put it in fields. So the capacitor puts it in an E field, and the inductor puts it in a B field. All right, so RC-DC circuits, so RC, that means resistor and capacitor, and DC means the kind of current. So it just means if you have a battery, a resistor, and a capacitor, and you hook them up in series. So you have those, and then it's going to follow these equations. So tau is equal to R over R times C here. And so it depends on if it's charging or discharging. If it's charging, you use this equation. And when I say charging, I'm referring to the capacitor here. So you use this equation to describe the amount of current on a capacitor as a function of time in an RC circuit. And then if it's discharging, so the capacitor has some amount of current, and then it's allowed some amount of charge on it, and then that charge is allowed to flow away. Then you use this equation to describe that. So notice that they're pretty much the same thing, but except for this one minus there. And then you can take the derivative of this to find this, but it's the same idea. Okay, so now we're on to something that's a little bit weird. Magnetic fields behave a bit differently than what we expect because of the weird directionality. So first things first, the force law for magnetic fields. F is equal to Q times the quantity E plus V cross B. So first things first, what is a cross product? Remember, a cross product is given by the direction of it is given by the right-hand rule. So if I have my velocity going in this direction, I point my forefingers in that direction, and I have the B field pointing towards you guys, then I'm gonna curl my fingers towards you, and that means that the force due to that, force on a charge due to the B field is gonna be pointing upwards because my thumb is pointing up. So that's the right-hand rule. Hopefully we're pretty comfortable with that, but just keep in mind that these two things have to be vectors, and and the magnetic force acts on charges. And also, a useful fact to have in your back pocket is that the magnetic force actually never does any work. So if you need to if you're worried that maybe if I have a particle that goes into a region of magnetic field and starts rotating, is it going to slow down at all? The answer is no, because the magnetic field can't do any work on that charge. So you're allowed to say, well, it's moving at the same speed as it was before, but now it's moving in a circle. It's being curved. Okay, so dF is equal to IDL cross V. This is saying the same idea here, but instead we took this Q and brought it into this E, and we said, we took this V and kind of we're neglecting the E, so the E is going away. We're saying we don't have an E field, and now we're bringing this V times Q. That's just I, right? The charge moving is going to be a current. So a moving charge is essentially the same thing as a current. So we're just saying I is now that, and then DL in a certain little bit of direction, and you cross that into V. So don't get intimidated by these differentials here. All they mean are little chunks of a wire. So you take your wire, and that wire might be really curvy and complicated to describe. And so the B field acting on a certain point here might be different than the B field acting at a certain point here on the wire. So the way we account for that is by chopping the wire up into tiny little bits and then saying, okay, I care about the B field at this point and then the B field at this point. And we work in differentials, and then we integrate over the whole wire. So oftentimes that you don't have to worry too much about that because integrals end up being easy, but that's the idea. So this is the definition of magnetic flux right here. So notice it's an area integral. You're integrating over an area. So it's essentially the same idea though. Remember, flux is just an area vector dotted into a field vector. So the radius, if you have a particle, that's what this formula right here is describing the radius of curvature, the radius of the circle that a charged particle will make at a certain velocity in a certain B field. So that's all that is. And you can rearrange, if you have no E field, you can always get this equation from just saying F is equal to mv squared over R. But you don't have to because you have it. So this is the definition of a magnetic moment. So it's just the amount of current times the area that current is enclosing. So oftentimes it's a circle. So it's just the magnetic moment associated with this circle is just the current going around the circle times the area of the circle. That's essentially the idea. It's not too complicated. They don't give you something that's they don't give you complex geometries. It's gonna be a square or a circle. The important thing to keep in mind for these magnetic moments is that the torque on them is given by the cross product into the B field, and the energy is the negative dot product. So that minus sign is actually very important. You want that minus sign because that tells you that the idea behind this equation is saying that the magnetic moment wants to be aligned with the B field. So if I have a B field pointing this way and a magnetic moment that's pointing upwards, then my magnetic moment is going to feel a torque on it, not a net force, because the net forces end up canceling out, but it's going to feel a torque, and it wants to align itself with the B field. That's what the minus sign is accounting for. Because remember, potential energy wants to be a minimum. So to do that, it must be at the biggest negative value. And that happens when those two vectors are aligned. So so now we move on to this equation right here. So this is B is equal to, so this is describing the B field due to a moving charge. So if I have a charge with a certain little point of charge and it's moving with a velocity V, and the charge is Q, then I'm going to use this formula right here to describe that magnetic field. So if I have a charge and it's moving to the right, it's going like this, then the B field is going to swirl around it, but it's going to depend on how far away I am from it as well. So that's why there's an R squared here. And you need to be careful because you're crossing it into R hat. So R hat is just a direction. So the magnitude of that vector is always going to be 1. So you can rewrite that as by bringing the magnitude down, and you have an R cubed on the bottom. These are the same formulas. They say the exact same thing. All it is it might be easier to work with this one right here. So now we move on to this very intimidating equation. dB is equal to mu naught over 4 pi times dl crossed into r hat over r squared. So this looks scary because it's got this differential here and a cross product. It's not as bad as it looks. So first of all, Biot-Savart law is probably not going to be like, you're not going to have to do a full integral using Biot-Savart on this test. I think that's likely, but don't count it out. It can happen. The idea is, so again, same here. It's complicated to describe the full geometry because there might be curves in there and the vectors can change. So to deal with that, we break things up into small chunks. That's all this dB means. So instead of the total B field due to a wire, so this equation applies to the B field created by a wire. So that wire might be bent into a complicated geometry. And if that's the case, then you have to use this equation to describe it. So we say a little bit of B field due to a little bit of the wire is given by this right here. So essentially, it's the same thing as this equation. It's just now we have a DL instead of a VQ. IDL, sorry. So it's exactly the same idea. All right, so now we get to Ampere's law. So Ampere's law is it's a nice, pretty way of encapsulating what Biot-Savart is really saying. All it is, so it's got this closed loop integral, and it's B.dl, not B.da. So it's B.dl, which means you just draw a loop, any closed loop, and then you integrate over that loop, and that's equal to mu naught times the I enclosed inside of that loop. So I enclosed, you need to be careful with like the directions. If you have two wires that with currents flowing in opposite directions, and those two currents are equal, then the I enclosed is net zero, right? Because the currents going in opposite directions are going to cancel each other out. So that's the idea. In this class, you're only ever going to need to use this to calculate circulation integrals. They're going to say, what is the circulation? What is the value of this integral? So you're going to have to count up how much I enclosed there is. Or you're going to have to use it to say, like, you just draw a loop and then you multiply. This integral is just going to end up being a circumference of a circle or something similar to that. Maybe the perimeter of a square, something like that. You're never going to actually have to do these integrals. So now we have useful formulas for B fields right here. I'm not going to go over all of them. Just remember, a solenoid is, it's just a long spring. So it's shaped like a spring, right? It's a coil of wire. That's what a solenoid is. And a toroid is just take that and then wrap it in on itself. So it's a donut shape. That's what it is. And the B field due to a loop is this, but this only applies along the axis that the loop is on. So if I have a loop like this, then my I is where the axis is. So that's what it's referring to. It's very hard to describe the B field off that axis. And then F over L is just the force per unit length of on one wire due to another wire. So that's what it's referring to. So if I have two wires, then the force on one wire due to the other wire is going to be given by that formula there. Okay, so it's already 6:52. My mouth is dry. Okay. I'll try and go quick, but hopefully this is helpful. I know this is a lot of information to throw at you guys at once, so ask questions if you have them. All right, now we're to induction and inductance. This stuff is intimidating, but it's not as bad as it looks, I promise. So what is this one saying right here? This is just saying if I have n loops, so if I have n loops, then and the magnetic flux through them is changing, then the EMF inside of those loops is going to be given by the time derivative of the magnetic flux times n. So if you have a changing magnetic flux through a bunch of loops, then the EMF or the voltage due to that change is going to be described by that equation right there. So don't get intimidated by this. Like, the idea behind whenever you see a d flux integral, so if you ever take the derivative of flux, all you want to do is just write down the flux as a function of time and then take the derivative of that. That's the easiest way I've found to do it. So yeah, hopefully that's helpful. And then this is actually saying the exact same thing right here. It's just for the case where n equals 1. So this is saying E dot dl over a closed loop, and that's exactly what V is. So E dot dl over a closed loop is exactly the same thing as V, right? The line integral of E over a loop over any line is really a voltage. So this is actually saying the same thing. It's just this is the differential form of Faraday's law of induction. Or sorry, not the differential, the integral form. So this equation is intimidating, but it just says if you have some charge, like if I have a bar, right, a metal bar, and it's moving through a magnetic field with a constant velocity, you're going to use this equation to describe it, but this one is very hard to work with. So I don't like using this one, but all it is, it describes if you have a bar moving through a magnetic field, then that bar is going to get some induced EMF on it, and it's described with that equation there. So now we have, this is Ampere's law, and I believe this is Ampere's law. We haven't actually gotten to this yet, so they changed the structure of the course, but it's on here, so I'll talk about it. So this is saying the B.dl, the circulation of the B field, is going to be given by mu naught times the enclosed current times the displacement current. So these may be functions of time. That's why they're lowercase i's here. And this B.dl is just, it's the dot product of B into your circle. So what you're going to do is going to draw a circle around some sort of current, and then the B.dl, circulation of that B field, is because B fields, like they look like turning vectors. The directions of that B field is going to be given by IC plus ID. And the displacement current is described by the change in the time derivative of the change in electric flux times epsilon, where epsilon is not EMF, epsilon is the, it should be the constant of permeability. So this is like epsilon naught, or whatever material you have. Very, very poor choice of symbolism there. So this is just inductance here. So there's kind of a lot of information in these equations here, but the idea behind inductance is, so like if I have a coil of wire, right? There's a lot of things that can affect how well this coil of wire is going to create some EMF when the flux through it is changing. So inductance is a way of quantifying how good something is at creating an EMF. So, if you're an EE, or if you're ever building a circuit, then you're going to take inductors, you're just going to plug it in, and this inductor is going to have a number associated with it. Stronger inductors have a higher L. So that's what it is. M is mutual inductance, L is just inductance. Oftentimes we don't have to worry about M. It's just, since it's the same thing, all it is it's like capacitance. It's quantifying how well this thing can resist this change in current. That's the essential idea behind inductance. And you calculate it by figuring out what is the flux through one loop of your inductor, and then you multiply by N, dividing out the current. So it doesn't depend, it's another geometric quantity. It doesn't depend on how much current is going through your inductor. All that matters is how it's shaped and how it's set up that way. Okay, so that's the complicated stuff, I would say. Now onto circuits. So if I have an LC circuit, so no resistor in it, and it's DC, so it's got some sort of battery in it. Actually, no. If I have a charged capacitor and just an inductor, then it's going to follow this equation right here. So no resistor, no battery, just a charged capacitor or a charged inductor, and then I hook that up to the opposite. Then it's going to oscillate like this. So this describes the charge on the capacitor as a function of time, and it might depend on omega there. But notice that this is the same frequency we have for resonance. So in an AC LRC circuit, resonance is right here. It's worth circling this and on your equation sheet and like making a note to yourself. This is the omega for resonance. If you ever see the word resonance in an AC LRC circuit, this is what it's referring to. So if you know what L and C are, you can figure out what resonance frequency is. So this equation right here it looks intimidating, but what it's describing is now if I have a charged capacitor and an uncharged inductor and a resistor, now I'm going to be losing energy through that resistor. So if I hook all those things up, then I'm going to have oscillation, but that oscillation is going to be going down. It's going to be losing power. It's going to be lower in amplitude as time goes on. So that's all that this is saying here. And the omega is given to you right here. So this is a charge inside of an inductor, and this is inductance for, so this is an L, not an I right there. So this is inductance for a solenoid right here, a long cylindrical solenoid. That should I believe that's what that is. But you shouldn't need that. This is energy stored in an inductor. This is energy density in an inductor right here. Okay, so now we're on the final section here, AC LRC circuits. This looks intimidating, but it's not as bad. So this stuff is separate from the stuff above it. This is just how to translate between Y and delta configurations of resistors. This was gone over in like semester before the first test. So don't worry too much about this. It doesn't come up on the exam we're doing today. And it shouldn't come up on yours. So here's first things first. Things to keep in mind with AC LRC circuits is that they behave surprisingly similar to regular circuits. We just need to be careful because now we have oscillation behavior happening. Instead of hooking our circuit up and then having constant current going through, now our current is going this way and then it's going this way, and then it's constantly switching between going one way and the other. So that's what's happening with this. So we abstract away from that by talking about RMS values and amplitudes, because those are much easier to describe. So the important things to remember is if you ever want to figure out the voltage drop across any particular component in an AC LRC circuit, then you use these formulas right here. So if I want to know the voltage across the inductor, I use I times XL, and resistance, it's exactly what we expect, is I times R. And for capacitance, it's I times C. But XL and XC both depend on the frequency. So if I increase the frequency, XC is going to go down. And if I increase the frequency, XL is going to go up. So now these values depend on how quickly I'm driving my circuit. So if I have a knob and I'm increasing the frequency on my source, then my circuit is going to respond by having a higher resistance to it, because XC and XL behave just like resistances. So E is equal to IZ, very useful. It's generalized Ohm's law. All it's saying is that this is the voltage amplitude. So EMF, so this is a voltage right here. This is how big the voltage can be. It's maximum, and it oscillates with the cosine, right? So that's what this E is referring to here. This definition of Z is very useful. You're gonna need it, so make sure you know where it is. This cosine of phi, this is worth writing down, this is the definition of what a power factor is. So cosine of the phase angle phi is what the power factor is. That is the definition of what it is. So the power factor is cosine of phi. So if you know what phi is, you always know what the power factor is. Okay. Just a few more equations. So if you figure out phi, usually from here, but you can figure out however you like by trigonometry. Drawing your phasor diagrams, if you ever need a reminder, that's right here. So IRMS is just the current amplitude. So that's the maximum value current can have divided by square root of 2. And same deal for VRMS. So the ERMS, you can always just write down IRMS times Z. So, very similar to this. It's just IRMS instead of ER and ERMS. So now we have this equation right here. It's surprisingly useful, but if you know the average power, then you can usually figure out what the power factor is, what I is, what E is. It's pretty nice. And you can always sub in this equation right here to any one of these three, and it'll give you different forms of the same relation. So that's very useful. And then these are equations that both of them are just talking about transformers. So transformers are kind of an afterthought. If you came to the session today, like an hour ago now, all it's saying is that the ratio of the turns is equal to the ratio of the voltages. So we have all transformers do is kind of steps up or steps down voltages. It's if I want a bigger voltage on one side, then I just have more coils on this side than I do on this side. So that's the essential idea. All they do is kind of transform voltages, hence the name. So here we have the same idea. It just says the power dissipated on one side of a transformer is equal to the power dissipated on the other. So remember, you have coils on both sides of a transformer, and then you have a B field that's kind of connecting the two through an iron core. So if this is an ideal transformer, if you're not losing B field anywhere, then the power dissipated here must be equal to power dissipated here, because otherwise you have you're losing energy somewhere, and yeah, that violates conservation of energy. Okay, so we haven't gotten to complex impedance yet. Yeah, so this is complex numbers, but most of what's happening here is encapsulated right here. I will say that. All right, that was a lot of information. I talked for like 35 minutes there. Does anyone have any questions before we get started on the actual exam? All right, well, if you guys do, just let me know. I will have my eye on chat for most of the time, but now we're gonna get into actual problem solving. So hopefully that was helpful. You know, you can always send me an angry email if I'm wasting your time with that. I will be sad, but I can take it. Yeah, so first question is a bit of a difficult one. So I know in the announcement I said I was going over 2020. Spring 2020 exam, but that's not happening today because the answer key does not have the multiple choice answers on it, and you don't have a blank version. So I was trying to make the blank version myself. I didn't have the multiple choice answers. I can't come up with plausible answers within a reasonable amount of time by myself. So we're going over fall 2019. So the second most recent exam. I'm sorry if this messes with your studying if you've already done it, and this is if this is not helpful to you. I very much apologize, but I can't I can't come up with all those answers by myself. So anyways, first question, Wheatstone Bridge. This is not as hard as it looks, but what we've got is configuration of resistors here. We're told that the current through the galvanometer right here, so galvanometer is a fancy word for something that measures current. We're told that the current through that is 0, and we want to figure out what R is. So I will give you guys until about 7:10. If you guys need more time, that's fine. But yeah, until about 7:10 to work on this problem. Yeah, let me know if you have any questions. There are a lot of you here. So odds are, if you have a question, you're not the only one with that particular question, which means you should ask it. And if it looks like I am uninterested and looking down, it is because I am going to start putting in attendance now. So if you haven't already, please put your net ID in the chat so that I can mark you down as here. Oh man. All right, so Christian got B. Yeah, in case you guys, yeah, I'd very much you guys like, let me try that sentence again. I would very much like you guys to share your answers with each other. It's a great way to learn. Having dissenting opinions and talking about how you got to your answers is very helpful. The whole idea behind SI is that you guys talk to each other, not necessarily just me. I'm not supposed to be like the expert in the room, but yeah. So Christian got B. I'm not going to tell you whether that's right or wrong yet, just because I want you guys to keep thinking. All right, so Caden got A, Christian got B. Does anyone else have answers yet? Don't fall victim to the bystander effect. All right, 2 more people for A. I'm going to give you another minute just so that, okay, I'm going to give myself another minute so I can try and get a few more names and not lose where I was at. Promise this will go a bit more smoothly once I have all these names in. You guys are, there we go, awesome. Okay, at 7-11, I promise I'll take a second off. Okay, 7-11. All right, thank you, Kurt, for doing that. Yeah, so this is way back at the beginning of the lectures that were being tested on. But it's surprisingly easy to solve this once you figure out that you can use not Ampere's law, you can use Kirchhoff's rules. That's the idea. So decent amount of you have answers. I want to try to get through a good chunk of this test. So let's run through this. Pull up the iPad. All right. Boom. Okay. So we're working on question 1 right now. Let me pull up the pen. All right, question 1. What we've got, let's sketch this out so we have a good idea of what's happening. I'm going to ignore the battery because it's not important for what we're trying to do here. All right, so we've got some currents and we also have this right here. We got currents running through these wires. So we'll label them with numbers since I'm sure that's what you guys did, even though that's not what I did in my notes. What was R3? 5. Okay, and R. All right, so that's what's happening. Now we've got to label some currents. So what we've got here, I'm going to label, actually, no, we're going to start right here. I'm going to label this as I1. And this is going to be I2. So these are just the currents that are running through each wire. So remember that you can only have one current running through one wire at a time. Nothing complicated like that. And this is actually equal to I2. So let's talk about why that is. So in general, this is not true, right? So I2 is equal to is the same for the 20 ohm resistor and the 5 ohm resistor. So we can talk about why that's true, right? And that's because we know that the current going through the middle, the galvanometer, is 0. So if that is the case, then we can say I1 is equal to I2 is the same at 20 and at 5. So we're allowed to do that because the galvanometer is reading 0. If that's not the case, then you've got a problem and your circuit becomes much harder to solve. But that is the case. And so just to be real explicit, right? So we have I2 coming into this junction right here. So we're applying Kirchhoff's junction rule. And so we know that 0 is going this way. So the only other place for the current to go is out. So you have I2 coming in and I2 coming out, and it's only one place for it to go out. So that's what's happening. Now we're going to draw a loop. So we're going to take a loop. We're going to go down, start at the very top of our circuit. We're going to go down, and then we're actually going to go across the galvanometer and up over. There are lots of loops you could have chosen to draw here. Let me do it in blue so that you can kind of see. So this is our loop 1. So we're going to write down an equation that corresponds to this loop. So that equation, we'll call it 1 in parentheses. So that equation says the following. So 20 times I2 is equal to, actually, let's do this in a more rigorous way. So we start at the top, right? So we don't have any potential. It's not like we're starting at a battery. So we have 0, and that is going to be equal to, all right, so we go down across the 20 ohm resistor. That's voltage drop. So we have a minus sign there. 20 times I2. And then we gain voltage because we go across the galvanometer, the middle wire, but there's nothing there to have voltage drop on. So then we go back up across the resistor, but we're going opposite the direction of current. So that's going to that's going to be a voltage gain because we're going opposite the direction of the current. So so it's the opposite of a drop. So 10I1. So we have this, so we can rearrange it just a tiny bit. We get 20I2 is equal to 10I1. So you may want to divide over some factors, and you could totally do that, but it ends up being nicer otherwise. So now we're going to do a second loop to solve this, and we're going to go like this. So, like I said, there are 3 different loops you could have drawn here, I think. But these are the 2 that are most straightforward, I think. So it takes some practice getting used to like being able to just look at a circuit and know which loops to use. So make sure that you are practicing, but it's okay if you didn't like look at this and know exactly what to do. All right, so we go across the middle wire at first, no voltage drop there. Then we go with I1 over R, so we have R times I1, and then we go up back to the top left corner, and that is we're going against, so we against current, so that's actually a voltage gain. In any case, that's wrong. That should be a minus there. Yeah, because you need a positive number. Well, you can take the absolute value at the end anyways. So you go up over that, so it's 5 times I2. All right, so we got 2 equations. I'm going to try to go a little bit faster because I know it's been 5 minutes already. So you rearrange this, you get Ri1 is equal to 5I. There should be a minus sign. That's what I messed up. So since we're going with the resistor, you have a voltage drop, and then you have a plus sign there. So that's why it's like that. Okay, so now we have 2 equations, and we're going to divide them. So I'm gonna flip this equation over. So I'm just going to take it and put the I1 on the other side, and then I'm going to divide them over. So that's what I'm going to do. So you got 20. No, not 20. 10 I1. Then we divide that by R. I1 is equal to 20 I2 divided by 5 I2. So you're allowed to do that. You can cancel out the currents, and so now we see it doesn't depend on the currents, and currents are not something we know, so we're feeling good about where we're going. So we get 4 is equal to 10 over R, which means that R is equal to 2.5 because it ends up being 10 divided by 4. So 2.5 ohms is the correct answer, which is A. So good job to those of you who got it. Hopefully, like I said, this problem is actually kind of a tough way to start, I think. But yeah, but maybe it's a good refresher. So if you have any questions, let me know. Otherwise, we'll move on to the next question. I will continue doing attendance. But this is asking about what is the circuit, the current in this circuit at different times. So specifically like the boundary conditions of the current at t equals 0 and at t equals infinity. I am doing a lot of talking today. All right, Soren thinks it is D. Awesome. Okay, I think I've got all the attendance taken care of, so I can be a bit more present now. All right, 3-3 for D. Yeah, because of the capacitor. All right. I like your guys' justification there. Always good to have reasoning behind your answers. Be able to explain why you think it's something. That's important. At least it helps me when I'm understanding things. Always asking the why behind something could be a very good way of really learning it deeply. But, I understand that this class is very difficult. There's a lot of stuff to learn, so you may not have time for that. All right. I'm getting a lot of good answers. Let's go through it. Is the correct answer D? Well, let's talk about it. So, I'm trying to figure out where chat so I can see the answers. All right. So we got this circuit right here, and at t equals 0, we'll start there. When we connect the switch, there's no charge on this capacitor, so it's actually going to act just like a wire. That's what happens. Capacitors just act like wires at when they're uncharged, right? Because they're happy to accept any charge, and it's once they build up charge that they start resisting that current going through them. So I2 is going to be non-zero, and I1 is also going to be non-zero. There's nothing stopping the current from going through there. Okay, so if we look at that, it means that it's either B or D, right? Because we said both I1 and I2 have to be non-zero, and only B and D have that t equals 0. Okay. So now at t equals infinity, now the capacitor is fully charged. So that means that it doesn't want to accept any more charges, and current is the thing that's pushing those charges on there. So the capacitor has got charge on there. It's not going to allow any more current to flow though, because it's like pushing against a wall. It's not going to happen. You can't shove any more charge onto those plates. So I2 is going to be 0, but I1 is non-zero, right? Because there's nothing stopping the current going through this loop. So if we have that, that means that I1 is non-zero. We have that right here, and I2 is 0, which is what we have. So D is the correct answer here. So good job, everyone. Looks like everyone who said something in chat was correct. So yeah, awesome. Very good. Now we can move on to number 3. We got another circuit here. And we want to know what is the current in the circuit delivered to the battery at 2 seconds. It's odd to think about current in the battery, but just as a reminder, I'm sure most of you guys know this already, but no session on Thursday. So usually I try and have the sessions on the days of the tests, just because they have good attendance and it's nice to have that many people there. But I might have 2 tests on Thursday. I'm not actually sure, so I don't want to have to deal with that. And also, you shouldn't be cramming that close to the test anyways. 1 hour before, it's not worth it, you guys. It's just going to stress you out.
Yeah, but what if you're already stressed out?
Well, you don't want to pile on, right? You can't, even if you're already stressed out, you can always be more stressed.
Yeah, but then you become so stressed that you're numb to the stress,
Yeah,
and then it doesn't
saturated.
bother you anymore. It just makes you sad.
You know, I don't think that's very healthy.
No.
Don't
But I don't think
don't
physics
let it
is
get to
healthy.
that.
Physics isn't healthy.
Physics is very healthy. It's challenging your mind. You know, if something physics is it's worth doing because it's challenging.
The only physics problem that I've truly enjoyed seeing, it was really funny. It was in like ninth grade, and it was Justin Bieber's thrown off a cliff at 9.81 meters per second. How long does it take him to hit the ground at a height of whatever? I thought it was funny.
There are many. I think I very much hope to change your mind, Kaya. Once we get to electromagnetic waves, I hope I can convince you otherwise. If you guys want to know what really would really, yeah, levitating frogs and magnets is fun. If you there are physics gets so cool after this course, you guys. If you want to, you can you get a physics minor. So after you take this class, you can get like all you have to take is like a lab class and two 300 level physics courses. I highly recommend modern physics. Very cool stuff. You get to see a superfluid. Like you can see liquid helium behaving like a superfluid. It's really cool. And you get to see the Meissner effect, like levitating magnets. It's awesome. I mean, Astro, it's not fair that Astro is like the sexiest subject in physics because there's so much cool stuff happening outside of Astro, but Astro gets to claim everything because the thing that
Because
annoys
it's
me
the
the
coolest,
most,
though.
it is very cool. I can't deny that. Like black holes, space, and
Like,
all
that
the.
stuff is so much more interesting than this. I
But
know it
you
has to
can't
do with
understand.
this, but still.
You can't fully understand what's happening in the sky without fully understanding,
I forgot we were doing the problem.
Yeah, Jonathan makes an excellent point. You do have to understand this stuff. Like there's a meme in Astro, and it's if any time you have a magnetic field, no one has any idea what's happening, and you can't neglect them because they're probably very strong. They're like what causes flares in stars, and like magnetic fields are the only way, and they're super complicated. Like magneto, it's actually plasma dynamics. Okay, yeah, I'm getting very distracted right now. I'm gonna take a step back. Stop gushing about science, specifically physics. All right. So, Caden, C time constant is RC equals 2.7. I naught is 333 milliamps. So I of 2 is 159. All right. Does anyone agree or disagree? I'm not going to tell you whether that's right or not, but I will. I appreciate Caden. You are. I appreciate your specificity there.
Imagine not getting distracted.
Yeah, it's pretty hard, isn't it? So the RC is just a definition. So RC is the tau on the equation sheet. It's the time constant. It's R times C, literally the resistance times the capacitance. So Kurt, another thing that may be confusing you is that you have more than one of each, so you can actually. The trick here is thinking about how these things interact with each other. And that's as much as I'm going to say, because otherwise I feel like I'd give away the answer. All right, I'll give you guys about 2 more minutes on this, but at like 7:31, we'll run through it. What was I saying? Yeah, so yeah, that would do it. Okay, so people are getting answers. Yeah, just 1 more minute and then we'll go through it. Awesome. Okay, getting some agreement. My roommate is cooking right now, you guys. It smells so good. Yeah, but if you guys want to get a physics minor, it's not that hard after this class. And you could take modern physics, and you only have to take like 1 semester of that, along with like 2 semesters of another 300 level class. Modern physics is a really fun class, and the professor is the nicest man. His name is Dr. Adam Kaminsky. Super cool guy. He's from Poland. He wrote me a letter of recommendation. He's super fun.
Iowa State doesn't seem very nice to non-physics majors. Just gonna put that out there.
You know, I can't disagree with that, unfortunately.
Oh.
Yeah, okay. So it's 7:31. Are we okay if I run through this on the iPad? Does anyone want more time? Yeah, that's true. I mean,
Yeah, but still.
yeah, engineering is definitely it is a harder major. Yeah, like I see what you guys have to do. The workload is insane. It's just physics is mind-bending. Like I did a whole unit on relativity. I still don't understand pretty much any of it. But anyways, that's not why we're here. We're not here to talk about relativity. We're here to talk about circuits. So first things first, we're going to draw a diagram of what we've got. So always label things generically if you can. So that's what I'm going to do. And I recommend you do the same when you solve problems, just because it makes the math a little bit prettier and clarifies what's happening. So what I mean by that is I'm going to just write down symbols for these components of my circuit. So I have C1 and C2 here. So here's the deal. In order to find RC, we have to reduce these down to equivalent capacitors and resistors. And yeah, so to do that, and the reason we're allowed to do that's what I should be saying, right? So why are we allowed to reduce these down when like that might affect the parallelness or the seriesness of the circuit. So we're allowed to do that because like the current doesn't care. The current doesn't care what it hits first, right? If I'm an electron and I'm traveling along here, well, like the thing that's causing me to slow down is not the fact that I hit a resistor. It's not like I'm traveling a certain speed and then I hit R and slow down. It's that I leave here and I'm moving with the same speed as I'm going around the entire circuit. And that's because like my electron friends that are also moving at the same speed. And I want to be as far away from them as possible. So that's what's happening in the circuit. So that's why we're allowed to do that. So let's figure out the equivalent capacitances. So these are 2 capacitors in parallel because they branch out and then branch back in. So they're on separate branches. That means they're in parallel. So C1 plus C2 is going to be our equivalent capacitance. So CEQ is just C1 plus C2. And we have 2 resistors in series, right? Because once we collapse down the C1 and C2, it just becomes a capacitor. So it's So they're in series. So the resistors are in series. So they're really easy to combine as well. So R1 plus R2. Okay, awesome. So now we can figure out what our time constant is. So it's going to be R equivalent times C equivalent. So you can plug that into your calculator. I'm not going to do that now, but now we're going to use the equation. So it is, so we want to describe the current. So we only have 1 equation for that. So I'm just going to write it down. This is on your equation sheet. You don't have to have this memorized. So we got to figure out what I naught is, and then we're good to go because everything else we know, and we know what time you want to plug in. So I naught, right? So we can just think about what's the behavior of the circuit right when you turn it on, and when that happens, the capacitor is going to act like they're not there. They're act just like wires because they don't care. They don't have any charge built up on them. They totally allow current to flow through them. So what we could say is this is equal to the total EMF of the circuit divided by the total resistance of the circuit, right? Because if I were to cover up these things, right, then I would just have two resistors in series. So the equivalent resistance between the two is just R1 plus R2. E to the minus T over tau is equal to I of T. So I could plug in any time I wanted into the circuit. It doesn't have to be 2 seconds. It can be whatever I want. But when I do, like it's just a matter of plugging in numbers to your calculator now, because we remember that this is R equivalent and C equivalent. So when you plug those numbers into your calculator, you should get 0.159 or somewhere in that ballpark, which is approximately 160 milliamps. So the correct answer is C. So good job, you guys. Yeah, any questions on that? All right. This is a nice conceptual question, maybe a palate cleanser. If those exist on tests, I don't know. But yeah. Christian, you might want to check your power. Note that the check that C is in millifarads or whatever it was. I think it's microfarads. Yeah, this is millifarads, so it's not micro. Yeah, if it's not an order of 10, I'm not sure. Yeah, so C was the correct answer. But so for this one, we've got some magnets. We don't know which way they're going after they're allowed to slide. All right, thank you for coming, Caden. Always a pleasure to have people show up at all. Yeah, but I hope I was helpful. All right, 2 for C so far. C is a pretty neat letter. It is. It's a nice letter. Oh, great icebreaker. What is your favorite letter of the alphabet? That's a good one. All right. And so far, it's unanimous in C. I'll give you guys a few more seconds to think about it. You hate the letter W. Of all the letters to hate, why W? Oh yeah, Q is a high tier letter. Absolutely. I think Q does not get enough love. X is the
reason for W is top notch. Whoever said that, I wasn't really paying attention to names, but that is the best reason to hate a letter.
Yeah, especially since it's not even right. It should be double V, right? Yeah, yeah.
It depends on how you write it, though. Some
No,
people make them a little curvy.
No, if you make it curvy, you're writing omega, and that's a terrible mistake. Don't do that.
Well, if you make it curvy, then you also have to angle the outside parts in to make omega.
That's not how I write my omegas.
Well, that's a different problem in itself.
You're right. Okay, so seems like most people who have answers have answered. So we all think it's C. Everyone said it's C. So let's walk through how do we do this. This is an odd question. I don't really know why they have it on here, but so first one, it's got the north poles facing the north right here. So like poles repel each other. North doesn't want to be near north. It wants to be south. Wants to be near north. So this is going to be pushed away, and it'll be pushed away even more because this one also it has a field that affects this one as well, but it's further away. So it's weaker, but also pushes it away. So we know 1 is going to the left. So immediately we can rule out A, B, and D. So now we have 2 right here. This one is being pushed away from magnet 1 and pulled towards magnet 3. So it wants to move to the left. No, that's the right. Sorry. And then 3 wants to go to the right, because north and south are facing each other. It'll be pushed away by this one, but it's further away. So this force is going to be stronger, so it'll still want to go to the left here. So the answer is 1 is to the right. No, to the left. Sorry. 1 is to the left, 2 is to the right, and 3 is to the left. So C is the correct answer. Very good, you guys. Man, I wish I thought of this icebreaker earlier. It would have been perfect instead of, I don't even remember what I did before the exam review. All right, so this one, it might be a bit tricky. We've got a proton moving in a circle, and they give us 1,200 revolutions per second. We want to know what the strength of the magnetic field is. So I'm not going to give you any hints unless you ask for them. So I'm going to give you guys at least 2 minutes before I even give any sort of hint whatsoever.
I have a question about the right hand rule.
Go for it.
Because sadly, I'm still confused. It might be easier. Let's see. Because if I have my camera on there, so if the current is going this way, and you point this way, and then you curl your hands, does that mean that the magnetic field is going up, or is it going down?
Well, it depends, right? So what's really happening is the B field wants to curl around that the wire. So if you have a wire with current going in a certain direction, the B field is going to make closed loops around that wire. So it depends on if you're looking above, right? So if I have my finger and I curl my fingers around it, then above the wire, then the B field is going to be coming out towards me, right? If I were to take a cross section, and the B field is coming out towards me above the wire, but below the wire, then my 4 fingers are pointing in the direction of the B field. They're pointing into the page. So above the wire, out, below the wire, in. And
then would it be easier to use this one instead?
I don't remember how to use that one, but it's individual. It depends on what makes sense most to you.
Because all I remember is A cross B is this one. So this is A, this is B, and this is A cross B.
Yeah, so it would be I cross R. So R will be out, so that's not right though. Yeah, no, yeah, I mean that works too. Take A in the direction of the current. B would be the direction of R, right? It has to be B cross R, I cross B. I don't know. I don't remember how this rule works, so that's why I don't teach it. I'm sorry. I think the way I always think about it is like if you have a wire, the wire is always sitting in the plane of the page, right? So whenever you're doing a problem, you always have a plane, the page sitting in, right? So the wire sits in that plane. And then the cross section. So you think of the page as doing like a cross section of the wire, and then that wire will divide the paper into an above section and a below section, and that's why I say above and below. That's what makes sense to me.
So then, if you point your thumb using the curling method, if you point your thumb in the direction of the magnetic field, then your fingers curl in the direction of the force?
Of the B field, not the force.
Wait. When do your fingers curl in the direction of the force?
That's when you take the cross product of V into B. So if you have a wire, that's going to create a magnetic field. But in order for something to feel that magnetic field, it has to be moving, right? Because remember the equation for force due to a B field, has V Q times V cross B. So if V is 0, then F is 0, right?
Okay, yeah.
So you have to be moving. And so this right-hand rule, pointing your thumb and curling in the direction of pointing your thumb in the direction of current and then curling your fingers around that gives you the B field direction. Once you have the B field direction, though, the force is going to depend on both the B field direction and the V direction, the V being velocity. So if I have a particle that's moving this way with the current, same direction as the current, and the B field is going to be and it's above the wire, so then I have V, and then B field is above the wire, is crossed into the B field coming out at me. So I have V, 4 fingers here, and then I curl my fingers towards B. So B is coming out at me, so I curl them this way. So the force would be down on that particle. So we really had to apply the right-hand rule twice. We had to do one to figure out the direction of the B field, and then another to do the direction of the force. Jeez.
Okay.
Yeah, the right-hand rule takes some getting used to. It might be helpful. I uploaded a video on my YouTube channel of of me walking through how to use the right-hand rule to figure out Lenz's law. That might help you. Like direction of induced current, that might help you as well. Because I have a wire, so it's not me pantomiming everything. I have like actual thing that I'm using. So that might be helpful as well. If you go to, I can link it to you if you want. Otherwise, yeah. Was
Okay,
that helpful,
I thought that
Kai?
you could only do
just
like the right-hand rule like once, or I thought that you were supposed to do it like once in order to find these things.
Well, well, it kind of depends, right? So if you're trying to figure out what the B field is, then yeah, you only need to do it once. But if you want to figure out what the B field is and then what the force is on something due to that B field, then you have to apply it twice. Think of the right-hand rule as just, it does the direction component of the cross product. So whenever you have to do cross product, use the right-hand rule to tell you which way that vector is pointing.
Okay.
Hopefully that helped. I understand that if it didn't, I need to work on my explanations for the right-hand rule. How are we doing on this question specifically? I know I said I would give you guys a hint after about 2 minutes. It's been more than that. And I suspect some people are stuck. Is that the case?
Alright, peeps.
Yeah, questions are good. I very much would rather spend lots of time answering questions than going through a bunch of questions, because me throwing answers is much less helpful. Okay, yeah, that's what I suspected. That's okay. So here's the deal. We're gonna try and work through this together. More stuck than ever before. Christian, I just want to make sure, are you more stuck because of the conversation I just had with Kaya, or is it just, or like, can I know what the cause is? That's what I'd like to know. So the way we start this problem is by thinking about what is the direction of the B field. So sketching out a picture is very useful. I am going to try and annotate. I don't know how well it's going to work. We have a circle, right? And we also know that the B field is moves in a circle perpendicular to the uniform magnetic field. So we're going to say, without loss of generality, that the B field is coming out at us. So this is the circle that the proton is making right here, and we're going to say that the B field is coming out towards us. So, you know, they don't say specifically this is how the B field is. They just say the circle is in a perpendicular plane. So, you know, you could rotate this, play around with it however you want. It just matters that this circle lies perpendicular to the B field. That's what's important. Okay. Yeah. So we have this, right? And now we want to know what the strength of the magnetic field is. This requires 221 concepts. That's why I think this might be confusing. Is you gotta remember things about central motion, right? So when things move in circles, we have nice equations to describe them. So let me just write them down. Yeah, I don't expect. I'm sure you guys forgot. There's nothing wrong with that. So I will just say the centripetal force F(c), so the central force that keeps things in circular motion, is given by the mass times the velocity squared divided by the radius of the circle. Yeah, I mean, I understand. I definitely understand. I understand that this stuff is not like in the forefront of your mind, but 221, it will come back. Like even in your engineering courses, you guys are gonna need lots of classical mechanics. So yeah, you're gonna need to know. I guess most of the stuff, if you're doing civil engineering, nothing ever moves, right? Yeah, statics. Yeah, fair enough. The good
Statics
news
is all of physics 221 or whatever that one is, basically.
I thought nothing moved in statics though.
Well, like, I don't know. It not necessarily, no, because it's static equilibrium, but it's it all has to do with forces.
Yeah.
And then the idea of something moving around something else.
I see. Ugh, that sounds disgusting, Christian. No, thank you. Yeah, the Platonic world of physics is much more nice. You get the principle of the thing, and you're done.
Hold up, friction? What? Since when is friction in statics?
Well, you have static friction, if you may remember. Yeah, coming soon.
Oh Lord.
Yeah, static friction is that's the thing. Friction is complicated, you guys. Real complicated. All right, so Nick is asking, how do we solve this? 6. The answer is B. All right. Let's go through this. I don't think that this is my explanation was super helpful. So let's go through this. It uses 221 concepts, so and I would expect something like this to show up. The good news is you have the 221 equation sheet is on your equation sheet. So if you find your equation sheet on Canvas, if you scroll all the way to the bottom, they've included the 221 stuff. So you don't have to memorize mv squared over r. That's there. But let's talk about the physics of what's happening, and then we'll throw some math at it. So let's resketch what we've got. So remember, what we're looking for is the magnitude of the B field. That's our end goal. What is B? B equals question mark. That's a question mark. So we're gonna sketch out what's happening. We got a circle, and our proton is moving in that circle. All we know is it's moving in that circle. We don't know the direction or anything like that. We just have R, and the proton is moving. It's got a certain speed V. So remember, the magnetic field doesn't do any work, so V is constant throughout the whole thing. So you don't have to worry about that. All right. So let's sketch the forces acting on this particle. All right, we're done. We sketched all the forces acting on this particle. This is a particle, so its mass is negligible, meaning we don't care about the force of gravity or anything complicated like that. There's only one force acting on it, and that's the magnetic force, FB. So if we can describe that force, we'll be good to go. So FB is equal to Q times V cross B. So this is just, we're not told about an electric field. I said electric field, I wrote it. We're not told about electric field, so we're allowed to neglect that part of the Lorentz force law. So we have this right here. And we also know that we already know the direction of the force. So we don't need to worry about the directionality of the cross product or anything like that. So we can simplify this formula considerably because we know that V is perpendicular to B all the time. It's orbiting in a circle that sits perpendicular to the B field. So we can say that this is just Q times B times B. We're allowed to do that because because we've already accounted for the direction. We know that the direction is pointing in towards the circle, right? Because otherwise it wouldn't be moving in a circle. So that's the direction of the force. It's pointing towards the center of the circle. That's what really matters. And we know that they're perpendicular, so we don't have any sine theta because sine of theta is 1. Okay, so awesome. We've got that. Now we would like to slot in FB, right? So it's a central force. So this is where the 221 stuff is going to come in. We have mv squared over r. So it should be big R. And that's going to be equal to our central force, right? So it's the only force in our problem, and it's pointing towards the center. A central force is described by mv squared over r. Centripetal acceleration is caused by this magnetic force. All right. So we can do a bit of algebra. You see v cancels out from both sides. We're looking for b, so we're going to divide over q to the other side. So m times v divided by q times radius. Hey, we have momentum up top. That's just a neat trivia fact. You get momentum up top when you do that. That's cool. Nothing special there. So now all we got to do is figure out what v is, because we know what everything else is. They tell us about the radius of the circle. Actually, they don't. But it ends up canceling out, interestingly enough. So let's focus on describing v now. So we're told we go 1,200 revolutions per second, right? We know we're revolving around a circle of radius r. So one revolution has a distance, right? Revolutions per second isn't a useful number to us. We want meters per second. So if we want meters per second, we got to figure out how many meters are in one revolution. Well, one revolution is just one time around the circle, and that's going to be 2 pi times r, right? So this is equal to 2 pi times r meters, right? Because r has units of meters, divided by 1 revolution. We can cancel out these units, and then we get some number out of this. And then we have a unit of meters per second. That's equal to v. So 1,200 times 2 pi r m, 2 pi r is in meters of seconds. That's equal to rv. So we'll call this number a, just to keep our formula simple. We have m over q times, and we're going to keep this r right here. So v, we're going to plug in, right? So it's going to be a times 2 pi r. We can cancel out that r, and now we're looking good, right? Because we don't know what r is. All right, so now we can just simplify our formula, bring this a out front, and 2 pi, I guess it doesn't really matter. And then we divide by q. So I'm looking at my notes here. Oh, yeah. Yeah, so then we should get the right answer out of this. Except you need to label, a is omega here. I'm just trying to make sure I didn't forget anything. 2 pi a m q. Yeah, that's right. Okay, so this is the right formula. If we plug in all our numbers where a is 1,200, then we'll be good to go. We'll get the right answer. So the right answer ends up being 7.87 times 10 to the negative 5th Teslas, which is answer E. So, let's take a step back and remember how we got this answer, right? So what we did is we started by sketching a diagram. Always a good idea. If you're absolutely, completely confused on a question, draw it out. Try and visualize what's happening. B rhymes with D. That's true, Eddie. It does. Yeah. So draw a picture if you're ever utterly confused, write down some equations that you think relate, and then work through some algebra. You might have unknowns, but working through things can clarify. And using units to guide your thinking can be very helpful, right? Because we needed this V. If we had plugged in V equals 1200, we would have gotten the wrong answer. And we would have had this R here that we don't know how to deal with. So you need to make sure that you account for that. So you need to be careful and use units to guide your thinking, right? You want B, units of Teslas. So Teslas require SI units on the other side. Revolutions per second are not SI units. Meters per second are. So convert revolutions to meters. So that's the idea here. Yes, the M is still just mass of the proton. That is a good question. Yeah, so Ethan makes an excellent point. What is the mass of the proton? I think it's on your equation sheet. Let's look that up together. No, it's not on your equation sheet for some reason. Charge of the electron is. Yeah, so I Googled it when I did it because it's easier to do that. Mass of electron is right here. E naught. Yeah, I guess you would have had to Google it. I apologize for that. And they're not going to do that on the test, though. I promise you won't have to Google things for the actual test. I mean, it might be useful to write down, because they might be like, oh, you could calculate it from X, Y, and Z. No one wants to do that. So it could be useful to write down, but yeah, I doubt they would give it to you. They'd probably just use an electron. Well, yeah, you're. Come on, you guys. I know it's difficult. This is another challenging problem. Got to think about forces. We've got a wire with a certain current through it, and they tell us the mass density. We want to know what is the magnitude of B field, as well as its direction, that will keep this wire suspended in the air. So I'll give you guys a few minutes on this, probably at least 5. You guys all can solve this, I promise. You have the tools and the know-how to do it. You guys just need to believe in yourselves. Have the confidence. Write something down. Promise you can do it. I apologize. I can't believe they don't have the mass of the proton on there. Like, it's 1.67 times 10 to the negative 27th, I think, kilograms.
These problems, it's almost like, yes, we're given the tools, but are we given the tools that make the most sense? It's like we're given a hammer and told to, like, I don't know, do a test with it on a piece of paper. Well,
Maybe, but part of the beauty of physics is that you can build the tools yourself on the fly, right? You don't have to memorize these equations because a lot of them you can rederive, right? Like every time I solve a problem, I'm rederiving an equation that describes that particular problem. So it's like you're building the tools on the fly, and I think that's kind of fun.
Who knows how to do that though? I don't know how many people in this room other than you that know how to do that.
I think if you practice, you'd be surprised. But yeah, I do recognize it's difficult, which is why the equation sheet is got a lot of stuff on it. Is because you're not going to rederive a lot of stuff. So I recognize that it's difficult, but you can do it. I promise. Also, keep in mind this is a weed out course. I'm not gonna deny that they definitely use this as a weed out course, especially the engineering department, since they don't want to. They don't want to like.
They don't want chumps in the engineering field.
Well, Yeah, like you guys already have a grueling program. They're not. They can only have so many weed out courses, and then they're like, hey, physics department, make sure you cover a lot of these topics. So the physics department, a lot of times is like, we'd rather talk about light for and optics for half the class, but we can't do that.
Yes, let's talk more about the aurora borealis and the physics behind that, because that's like the only thing that I will probably take out of this course.
Yeah, I mean, I think you will take one other thing away, and hopefully I can.
Yeah, but that's the coolest one.
Oh, you'd be surprised. Wait till we learn what speed of light. It'll blow your mind. Yes, this is going on YouTube, Ethan, just to answer your question. So it'll go on YouTube as soon as I can upload it, but it takes like an hour or so to process since I just have a crappy laptop. But yeah, so after the session, the video will be processed and it'll be uploaded to YouTube. And the link to the YouTube channel is on the announcement, and I will repost an announcement with the link on it so that you can all find it. I don't think I'll do that on Canvas though. So if you found me through Canvas, go to the SI website that I linked to on the Canvas announcement and bookmark that, because that's the easiest way for me to get in touch with you. Nick, you make an excellent point. Physics does get a bit easier after this class because like this is an overview of all of E&M. Like this is like getting, it's like the basics. It's like the E&M for babies is essentially this class, because I'm in an electricity and magnetism course right now. Like, and we're talking about radiation. The math you do in this class is heavy for an actual E&M class. But in this class, you don't actually have to do that heavy math. Thanks, Ethan. Okay, Eddie, sorry, all right, so Eddie thinks it's B. G over M is the grams per meter. Yeah, it's kind of an unfortunate notation, but it's just grams per meter. That's what it is. Oh my God. I haven't done this much talking in months. I'm very hoarse tomorrow. Well, I was gonna say you guys should take E&M. E or D, not sure which one for sure. All right, we're getting answers. That's good. I was expecting this one to go like the last one, but that's not happening. I'll give you guys like 2 or 3 more minutes, and then we'll go through this. Another. So here's another thing about the physics department at Iowa State. Dr. Paul C. Canfield, if any of you guys had took 221 with him, he is like the highest profile scientist we have on staff. That man like brings in bank for the department. And so they have him teach 221. And so they opt for like higher profile physicists to teach the low level courses, because then like you could say, hey, I'm an engineer and I got to be taught by Dr. Paul C. Canfield, PhD. So, and these professors are not necessarily the best teachers. That's not necessarily the case with this course, because she's just a teaching professor. Paula does an excellent job, but like the lower level courses, that can sometimes be the case. But with the upper level courses, you get really nice teaching professors who like to teach, because those courses are harder to teach. So but I'm pretty sure, don't quote me on that, but if you look at the Iowa State physics faculty under like teaching professors, then yeah, she's listed under there. So that means I'm pretty sure that means that she, like, her job is really just to do to make sure that people are getting taught, not necessarily, she's not like on staff to do research. She's just here to teach undergrads. And I think she might do some grads courses as well. Yeah, Paula is an amazing human being. She's great. All right, it is 8:10. How are people doing on this?
She also told me that she misses talking to students. So if you email her and ask her questions, or like ask her to have a Zoom call with you or whatever, yeah, she would like to talk to you.
Yeah, she's super fun, easy to get along with. Yeah, Paula is a really nice lady. And also Dr. Dushan and Dr. Danilvik, I always call him by his first name. That's unprofessional of me. And Dr. Shinar. Both of them are very nice as well. They'd be happy to talk to you, but they do research as well, so they're more busy and stuff. Dr. Dushan is actually an astronomer, so if you ever want to waste your own time, you can always just get him to gush about astro with you, because he would love to do that. He teaches Astro 250, I think. At least I think he is right now. He might not next semester. You guys are really good at getting me off topic. Or at least maybe I'm just not feeling like focusing today. But I want to focus in on this problem because it's a bit difficult. So how are we doing on this? Do we need hints, or do we want to go through it on the iPad? Can I get some sort of indication? Okay, my number one hint is draw an FBD. You draw an FBD, that can lead you to the equation that you need. And also, so it's complicated to think about this. Yeah, so most of them require length. My advice to you is let L be some arbitrary length and then divide it out at the end. You should be able to make your equations work out so that the L is going to come over to is going to cancel out, because you know what the mass per unit length is. So if you get an M over L, then you can just have that be your thing. Otherwise, you can always just assume L. You can work your equations. You can work your equations as like with an L in it, and then at the very end you can just say L equals 1 and then throw it out. That should work as well, because I did it both ways, but the second way is less rigorous. Let's go through it on the iPad. I want to make sure that we get through a decent number of questions, and I think my hints were not very helpful. All right, so it's 8:13. Man, time sure flies when you're having fun. So we're on question 6. It's okay if you guys are lost. So these are doozies of problems. Like they're pretty difficult. This one back to back with the last one, it's kind of mean. But what we're gonna do is draw an FBD. So we have two forces, right? We know that FG is pointing downwards. And then we have some sort of magnetic force. So we want our magnetic force to be pointing up. So first things first, we got to think about the direction of the B field, right? So the B field is either coming out towards us or going in towards the plane. So that's the direction of the B field. Which one is it, right? So we got to use the right-hand rule to do that. The current is going this way. So in my diagram here, I've got a wire, and the current is going to the left of my diagram. And I'm just like, this FBD is just concerned with one tiny little segment of the wire. So this FBD is not like the whole wire. I'm not treating the whole wire as a point. All I'm doing is like, I'm just gonna like, if I were to take a section of this wire, what is the FBD for that? That's the idea that I've drawn here. Okay, so I is going to the left. We got to use the right-hand rule to figure out what the direction of the B field is. So we want our thumb to be pointing up, right? Because that's the direction of our resulting force. And we take our forefingers, pointing in the direction of the current. So that would mean we have two choices, right? The force is either pointing up or pointing down. So we want it to point up. So we point our palm towards us, and we curl our fingers this way. So that means that the B field is coming out towards us. So it's V cross B. So B is coming out towards us. So B is coming out of the page. So yeah, the answer is either B or D. We got to figure out which one it is. We got to do a bit of numbers. So this, if we're concerned with just a little differential segment, our first things first, we're going to use the following equation actually, before we even use the FBD. In fact, I don't think we actually need to. So we say dF is equal to I dl cross B. So dl is some vector. B is coming out towards us. Well, dl is perpendicular to B, so we can get rid of the cross product and just multiply by the magnitudes. So it's IB dl. That's what we're going to do. That's equal to df. So we're dropping the vectorness of it because we already know the direction. So we're going to integrate both sides, and really the integral is just a fancy way of getting rid of the differentials on both sides. So our net force, our force due to the magnet is just IB times L. Because we're integrating dl from 0 to L. That's IB times L. So we want this L to not be in our final equation. This L should not be anywhere in our final answer because we don't know what it is, right? We know mass per unit length. We know that. We don't know what the length is. The length is not given to us, so we better hope it cancels out somehow. All right, cool. So we have this, and what do we want this to be equal to, right? What is the condition of F, right? So this is FB, right here. So we want FB to be equal to FG, right? That's suspending it in place. That's going to counteract the gravitational force. So we're going to say m times g, right? So m is just the total mass of whatever length we have. We don't know what it is, but like generically, it'd just be m times g. I times b times L. So we've got this equation, right? So all we're doing is saying the weight is equal to the magnetic force. So now, all we want to do is solve for b. So divide over I and L. We get m g over I L is equal to b. All right, well, now it's not looking so good, right? Because we've got an L in our final formula. Like there's nothing left here for me to substitute around. So things might not look too good, but you look at the formula, we see m times g divided, we can switch around I and L. And then we see m divided by L right here. And that's making us feel better because this is m divided by L. This is the total mass. That's what little m stands for here. Actually, to be extra clear, right? So m is not, it's not a little mass. It's the total mass of whatever length wire we have. So if we have the total length wire here equal to B, well, that's equal to m, our mass density. So if you remember from 221, our mass density was just mu. You could call it lambda if you want. So it's just amount of mass per unit length. So you multiply that times g. So g is gravitational constant, 9.81, and I is whatever the current is. That's equal to B, and we know what all these numbers are. So we're actually good to go. We can plug numbers into this formula. So when you do that, you get an answer of 4.9 Teslas, which is B. Are there any questions on that? So I know it's like, it seems like I pulled these out of nowhere, but like really it's just algebraic manipulations and thinking about what these symbols represent on the page. Don't get lost in the algebra. Think about what each step is doing and see it like what these letters represent. And then you can kind of tease out these relationships from what you're given. So I know this seems difficult, but you can do it. I know you can.
Actually, I have a really quick right-hand rule question.
Yeah.
So, like in this case, when we point our fingers like in the direction of the current, we have our thumb point in the direction of the force that we want, right? So upwards.
Yep.
And then what do we like curl our fingers in? That's supposed to be like the direction of the field.
Yeah. So we curl our these four fingers. They curl in the direction of the B field. So we
Okay.
know all we know is really that the B field is
Coming towards
It has
us,
to
right
be.
out of the page.
yeah because the ambiguity is now is it here or is it on the other side?
Okay,
So it has to be on this side.
cool. Thank you.
I think so. Then like that. That's a good question though. The right hand rule, I like. The right hand rule takes some time to get, and if you're not getting it yet, you're not the only one. People have struggled with this many times. All right, so it's 8:20. We got 10 minutes left. We're on question 7, which is okay. You guys all have access to this test, and I've gone through up through question 25. So if you have any questions on anything, you can message me if you'd like. I can try and answer them. Otherwise, just talk to the professors as well. So we can move on to this question right here. We've got a circular loop. They give us the area and it lies in a horizontal plane. They tell us the B field is oriented at this direction, and we want to know what is the magnitude of the torque on the loop. So this is a good question. This is a good question. Gets you thinking about something. I'm not gonna give it away yet, but it'll take about 4 minutes. That should give us enough time to get through maybe 3 more questions before the end of the session.
What would be considered like an outrageously large magnitude for the B field? Like if we get
anything
number,
above 5
anything,
Teslas is pretty unrealistic.
anything above 5? Okay.
I mean,
What about like the lower limit?
lower limit, anything like smaller than like nano Teslas would be unreasonable, probably. Like, are you looking for range, like just checks to see if your number is realistic?
Yeah.
Yeah, I say if you get anything higher than a better limit would probably be 10. If you're getting anything bigger than like 10 Teslas, then you're probably not getting anything realistic. And yeah, anything smaller than nano Teslas probably won't show up, but it's hard to say.
Nano is times 10 to the 9.
10 to the negative 9, yeah.
Okay.
I mean, there is the caveat though. Like, if they ever ask, like, oh, what if they could be like, okay, so here's a quark that has a third of the charge of a they could give you something really mean, because you can do a problem that's like, how fast does an electron need to spin in order to have a certain electric field or magnetic moment. My point is, it'll depend on the problem, but in general, you're working in the classical case, so you're going to work on problems where you have a realistically sized magnetic field. If you guys find yourself struggling with like conceptual ideas after today, a nice resource are the Feynman lectures. So I really like them. A lot of people who do Physics education say Feynman's just bad, but I think Feynman is fine. So you can just Google Feynman lectures. They're free online. They're free online, and you can look them up. And he's got a whole like volume about E and M, so you can read about them. And he does a really good job. He goes through the equations and all the math and stuff. So it's a nice way to kind of learn. Feynman does a good job of explaining. He's dead now. No one's giving me answers yet, so that's fine. I just want to make sure that people aren't just sitting around. Okay. Oh, Eddie, I totally did not see your answer. Sorry. All right, 3 people for A. Yeah. All right. Let's go through this. I won't say whether A is correct or not yet, but so far it's unanimous. So. All right. So how do we do this problem? First things first, we got to think about how to calculate torque, right? So torque is represented by tau, just like everything else in physics, which is dumb. So torque, tau, is equal to mu cross B. Actually, sometimes the symbol for torque is gamma, but that doesn't matter. Okay, so this is our formula. So this is the torque on a magnetic moment, mu. So mu represents the magnetic moment, B is the B field, and the torque on that is just crossing mu into B. All right, so we want to describe the magnitude, so I'm going to take the magnitude of both sides of this formula. The magnitude of tau is going to be the magnitude of mu cross B, right? But there's a nice identity for the cross product of two vectors, magnitude of that is. So it's the magnitude of mu times the magnitude of B times the sine of the angle between them. So we've got that. We have to be careful though, because theta is not 70 degrees, it is 20 degrees. Because if our circle is lying in this plane, like plane we're looking at, then the area vector is pointing up like this. So the B field is pointing to the side. We're given this theta, but what we really want is this alpha. We care about alpha, not theta. So we got to plug that in there. So let's even place that down there. We've got that. So it's mu times B times sine of alpha. And we know all of these numbers. Mu is easy to calculate. We can even expand mu. You can say that's I times the area times the B field times the sine of alpha. And now we really know everything here, and we can plug those numbers into our calculator, and you get 2.7 times 10 to the minus third Newton meters as the units of torque, which is A. So good job. Everyone gave me an answer, said A. So yeah, I think we are, yeah. So that'll do it for the exam review, I think. I am going to use the last 2 minutes to give you guys some advice on how to take this test, because I know it's difficult. So yeah, first of all, I want to pause. Are there any questions on anything not specific to like the questions we went over? Anything, any lingering problems that anyone wants to address? Give me a second to type that up while I drink my water. All right, well, no one's given me that. So I will just give you guys advice. So you, as Paula said, you're allowed to write your own equation sheet. So what I would recommend is at least printing this out if you can. So this equation sheet will be very helpful. It's got, like, there's too much information to memorize on here. So printing this out and marking it up yourself would be very helpful. Like circle these, say these apply to transistors. Highlight this and say this is the power factor. Stuff like that. That can be helpful. It'll save you time, so you don't have to worry about, is this actually the power factor or am I misremembering it? It'll save you time on the test. Precious time that you're going to need, because yeah, it's a time test. So just a reminder, you have let's look at the equation sheet real quick. So A radial is V squared over R. So F radial is M times A radial. So you have this. This will be useful. So highlight this, because this is probably like the only thing from 221 that you're going to need tomorrow. Not tomorrow, on Thursday. So yeah, highlight that. That'll be useful. Other than that, I don't think you're going to need much more. What else? What other advice can I give you? Stay positive. Don't go into this test thinking you're going to fail, because you're not. Drinking caffeine can be, it can help, but I personally get bad anxiety from caffeine, so I don't recommend drinking caffeine if that's what it does to you. You don't want a panic attack during a test. That's a bad time.
Oh,
So, yeah.
But when it comes to this exam specifically, like the concepts is what we need to focus on. And are there any resources when it comes to like the equation sheet itself? Just because it seems like some of the videos, the variables are slightly different.
I'm not sure for like specific resources for, yeah, I think the variables can differ slightly. Paula may have changed her notation. I think that the best way to solve that problem is to mark it up yourself. Like do what makes sense to you on your own equation sheet. I think that's best policy, because no one else is going to be looking at your equation sheet except you. So circle your equation sheet and like label things if that helps you. Do whatever makes sense to you to make sure that you can navigate it quickly and find what you need, because there's a lot of information here and you don't want to waste time going through it and trying to find things. As for concepts, I think you guys would be surprised how good you are with the conceptual problems. Like usually when you're solving physics problems, mistakes come from the math. Because the physics is, you can usually, I guess it depends on who you are, but like having a clear mental picture is a very good first step in the physics. But if you need to work on concepts, going to hyperphysics is an excellent resource. So if you go to hyperphysics, just Google hyperphysics, you'll find it. There's a whole electricity and magnetism part right here, and you can click on whatever you need to review. So, electric circuits, click on that. They've got all these concept diagrams for the load, but they've got I think they have an AC AC LRC circuit stuff here. Yeah, so let's go to inductors. Boom, like they give you EMF is L didt, stuff like that. So it's super useful. Hyperphysics is really nice for all sorts of things. Other than that, yeah, stay positive when you're taking it. Don't panic. You guys are going to do fine. Yeah, and also make sure your calculator is in degrees mode when you take it. It's really going to be a bad time if you plug in 40 and you get 40 degrees and you get out the wrong number and you get a question wrong because of that. You can't get those points back. So make sure your calculator is on degrees mode. I've taken a physics test in radians. Bad time. It's back in high school. Yeah, so I'll stick around for a few minutes, but it is 8:30 and I have a bit of homework I need to do. So I'll stick around for a few minutes. I'm going to stop the recording now.